Okay, our focus today is on finding roots and zeros of polynomials of higher order, not just quadratics, but higher order polynomials. So the first thing we can talk about is understanding the difference between zeros, factors, and roots. So C is a zero of a function. All these are equivalent statements. If C is a zero of the function f of x, then x minus c is a factor of the function f of x. And C is a root or a solution if you set f of x equal to 0. So in my mind, roots and zeros are very, very similar, and you can easily get them confused, but it doesn't matter because they essentially mean the same thing. But a zero comes from a function, but when you set the function equal to 0, you get your root. It's not that big of a difference, but I'm not going to hold you to it too strictly. So in addition, if C is a real number, like let's say you find a root is 2, then 2 comma 0 or C comma 0 is an intercept of the graph of the function f of x. So that's where it crosses the axis. So if we're looking at this function, x to the fourth minus 5x squared plus 4, we can see that there are 4 places that it crosses the x-axis. So we have at negative 2, at negative 2, negative 1, 1, and 2. So we can restate the zeros. The zeros are negative 2, negative 1, 1, and 2. The factors are x plus 2. Remember, it's always x minus r, where r is a root. So you're going to go x minus a negative 2, which is x plus 2. And therefore you have x plus 1, x minus 1, and x minus 2. So then the roots are, again, negative 2, negative 1, 1, and 2. And then this x-intercepts negative 2 comma 0. That's giving you the x and y coordinates of those intercepts, etc. Okay, you get the idea. So, fundamental theorem of algebra, which is written in this really complicated language, but it means a really simple thing. So I'll leave the complicated language, but here's what it really means. What it really means is any polynomial, let's go faster, any polynomial of n degree, so like a third degree or a fourth degree, has n roots, though some of the roots might be complex. So you might get real roots, you might get complex roots, but for any polynomial of a certain degree, you have that many roots. So if you have fourth degree, you'll have 4 roots. If you have seventh degree, you'll have 7 roots. Although some of them might be complex roots. Okay? And that's what all the rest of the complicated language says. So, looking at these functions, we can figure out how many roots are going to be. Take a look at the first one on the left. Obviously, x squared, there's going to be 2 roots. The one on the right, x to the fourth, there's going to be 4 roots. Let's go ahead and try to find them. So we'll start with the one on the left. That is just a simple quadratic. We can use a quadratic formula. Maybe it factors, but quadratic formula works every single time. So I get 8 plus or minus a square root of 64 minus 4 times 16. That's 4ac. 4 times 16 is 64. So that looks like that part of the term is just going to drop out. We're going to get 64 minus 64 is 0. So I get 8 plus or minus 0 is over 2. I have to go slow down. Which is 4. So I got 1 real root. That's actually a double root. So that kind of defies our fundamental principle. But that is the idea that you just have 1 root because it's a double root. So if you were to factor that, you're going to get x minus 4 times x minus 4. So it is 1 real root, but there is considered a double root. Okay, next one, x to the fourth minus 256. That I can treat, remember it's a binomial, and it looks to me like it has to be, we can only factor that if it's a difference of squares or a difference of cubes or a sum of cubes. And this looks to be a difference of squares because 256 is actually 16 squared. So if I could factor that, I'd say x squared minus 16 times x squared plus 16. And then I could factor each of those terms, or at least I could just, actually don't need to factor them, I could solve them. X squared is negative 16, so x is going to be plus or minus the square root of negative 16, which is plus or minus 4i. And then I can do the same thing with the other one. X squared is minus 16. Oops, that's weird, I got really small writing. X squared equals 16, x is plus or minus 4, which means you're going to get 2 real and 2 imaginary roots. So one thing to notice that imaginary solutions, that plus or minus 4i, they always come in pairs. You're either going to get the plus version and the minus version. So that's something that's helpful to know when you're trying to find roots or when you're trying to build equations from roots. Given the function and one of its zeros, find all the zeros of the function. So we played around with this last time. where you're given one root and then you find the depressed polynomial and you can find more roots from there. So let's go ahead and practice with this one. We have the root of x is equal to 2. So we're given one root, which means that x minus 2 is a factor. So let's use synthetic substitution to find out what the depressed polynomial is if we substitute that root in or divide in x minus 2. So we're going to set up our coefficients, and we're going to divide 2 into our equation. So let's go ahead. That's all set up. 2, 1, negative 4. All the coefficients are taken care of. There's nothing missing, no zeros I need. So we're good to go. Okay, so bring down the 1. 2 times 1 is 2. Add that up. Super fast. And look what you get. You get a 0 remainder. Hooray. And 0 remainder means that x minus 2 is a factor, which we already knew. But you've now got the depressed polynomial that's left over, which is x squared minus 2x plus 2. That is a quadratic, which means we can use the quadratic formula or factor it. We just use the quadratic formula so I don't have to think. 2 plus or minus the square root of 4 minus 8. 4 minus 8 is negative 4, so I'm going to get a complex number here. I can see 2 plus or minus 2i over 2, which leaves me to 1 plus or minus i. Now, I know I'm going really fast in these lectures, with the writing especially, so feel free to pause at any time to slow down or back up and hear it again. All right, keep going. Here's a complex conjugates theorem. It says, suppose a and b are real numbers with b not equal to 0, meaning b is, you do have a complex number. If a plus bi is a0, so if one of the zeros is a plus bi of a polynomial function, then a minus bi is also a 0. So they come in pairs. So a plus bi is a 0, then a minus bi is a 0. They're going to come together. So if you're given one of them, then you know the other one has to be there as well. And here is an example that is going to be long and tedious. I apologize for that, but that's how it's going to be. So use zeros to write a polynomial function. We're writing a polynomial function of least degree with integral coefficients. Integral coefficients just means they need to be integers. The zeros of which include 4 and 4 minus I. So if we know that 4 is a 0 and 4 minus I is a 0, then we know that because they come in pairs, 4 plus I must be a 0 also. So knowing that we have those three zeros, we can now write in factor form the three zeros, and then we're going to multiply them together. So we got x minus 4, that's 1 0. Then we're going to get x minus 4 minus I. And we have to be really careful with our parentheses to keep track of all of our signs. This is going to be, you have to be very methodical and careful as you do this. Okay, so x minus 4 minus I, and then we're going to multiply that by x minus 4 plus I. Okay, so you see got lots of parentheses and lots of minus signs, so I'm just going to say slow down, be careful, and take your time in multiplying these out. So I'm going to go quickly, but when you're doing your work, you want to take your time. All right, so I'm just going to look at the second two terms and go to simplify that. And when I do, I get x squared minus 4 plus I times x minus 4 minus I times x plus 4 plus I times 4 minus I. I basically just FOILed out those terms. And now I'm going to go through and distribute my negative signs and simplify and combine like terms, and I'll get x squared minus 4x minus ix minus 4x plus ix, and now the last two terms, will FOIL those out. I'm going to get 16 minus I squared. Again, I'm simplifying x squared, total of 8x's, so minus 8x, the ix's go away, and 16 minus I squared, remember I squared is negative 1, so minus negative 1 is plus 1. Wow, and so I did that wrong. And so that should be plus equals 17. Okay, so 16 plus 1 is going to be 17. So I'm going to get x squared minus 8x plus 17. Okay, so we'll add the 17 term. But now we've got to bring in the factor from before, that x minus 4. Don't forget about that one. And so we need to multiply the combined result we had before times x minus 4. I'm going to move it over here so I can do it more neatly. Remember, when I take a trinomial multiplied by a binomial, I like to stack them up so that I get everything cleanly and neatly multiplied. So I work through x squared minus 8x plus 17 times x minus 4, and then I'm going to add up my result, and I'll get one great big polynomial. Notice that the order of the polynomial, in other words the degree, is third. It's a third order, x cubed, which makes sense, right? Because we started with 3 zeros, 4, 4 minus I, and 4 plus I, and we wanted a polynomial function of least degree, least being x to the third, that has those two that we are given, plus the one more that we knew about, since the 4 minus I comes in pairs with its imaginary complex conjugate. Okay, another one like that. Write a polynomial function of least degree with integral coefficients, the zeros of which include 2 and 4i. This one's actually going to be a little bit easier. Well, 2 and 4i mean that if you have 4i, you better have a negative 4i also. So you're going to have the zeros 2, 4i, and negative 4i, which is 3 zeros, which means it better be a third degree polynomial by the time we're done. So let's go ahead and find our factors. We got x minus 2, x minus 4i, and x plus 4i. If we take each of those and multiply them, then we should come up with a polynomial. So this one's less messy for sure. We can go ahead and FOIL this out. We're going to get just the second two terms, x squared minus 4ix plus 4ix, which will go away, minus 16i squared, which becomes plus 16. Okay, now we've got to multiply that by the x minus 2 factor, though. Don't forget about that one. X minus 2. Now we'll FOIL those out. X cubed plus 16x minus 2x squared minus 32. That is my full polynomial. I'm going to put it in correct polynomial order with each degree term descending. So x cubed, 2x squared, 16x minus 32. And that is my final polynomial. Notice it's third degree, which is what we predicted since we have 3 roots. That's the fundamental theorem of algebra. Okay. Now, g of x, we're given a 0 of negative 3, find the remaining zeros. So this is where the rubber hits the road. This is what our whole goal is. We're given a 0, find the rest. We know how to do this now. We're just going to take, using our synthetic substitution, we're going to plug in negative 3 and see what falls out if we get a 0 remainder. If we do get a 0 remainder, we can keep going. If we don't, we have to stop. So we'll do our synthetic substitution, and lo and behold, 0 remainder, hooray. And we now have a reduced polynomial, which would be x squared plus x minus 30 equals 0. Now we could factor that, or we could do the quadratic formula. I'm just going to go ahead and do the quadratic formula. Negative 1 plus or minus the square root of b squared, 1 minus 4ac, 4 times 30, all over 2, which is negative 1 plus or minus the square root of 121, which is a perfect square. Negative 1 plus or minus 11 over 2, so I get 10 over 2, and negative 12 over 2, which is 5, and negative 6. Oh, what do you know? I could have factored after all. I would have factored and gotten x minus 5 and x plus 6. That would have given me the same quadratic. Sometimes there are multiple ways to solve it, but the quadratic formula works every single time, so if you're too lazy to even check to factor, you can use the quadratic formula. So my zeros are, remember I was given the first one, negative 3, then the other two are 5 and negative 6. So there's all 3 of my zeros, and we are done.